Okay, so this next example is about finding the correlation coefficient and interpreting R in context. Interpreting R in context is actually very much like doing what the fuds. It's just you don't have to mention outliers. So it's FDS, I guess. Form you assume is linear with R. So anyway, it's the strength and direction part. Okay, so, oops, let me turn that on. Okay, so I've already entered the data into list 1 and list 2. To get the correlation coefficient, you actually have to do a linear regression. And so this is kind of fast forwarding to chapter 7 because chapter 7 is linear regression, but we have to do this to find the correlation coefficient anyway. So we go, once you enter the data in list 1 and list 2, you go to stat, calc, and you do linreg. This is an older calculator, so it's not going to pop up with the menu, but in the menu it'll ask you like X list, Y list, and then I'm not sure, there might be something else, but then you just hit calculate. This one, since this is an older calculator, I'm just going to hit enter on number 4 and enter again. If you do not see this R and R squared, you have to go to the catalog and do diagnostics on. Okay, so if you don't see that, I'll show you how to do that. You go second, number 0, and then alpha is already on. You want to skip to the D's, otherwise you're going to be arrowing a long time. So you want to press the X to the negative first button to skip to the D's, and then you want to arrow to diagnostics on. All right, you have to press enter on that and enter again, and that's the only time you'll have to do that unless your calculator, unless the batteries die or something and your memory gets cleared, or if you have to clear your memory for some reason. Anyway, then if you go back and do the linear regression, you'll see the R squared and the R. We'll talk about R squared in chapter 7. So R here is 0.996. I would probably do at least 2 decimal places for R. So, R I'm going to say is 0.996. And then we need to interpret it in context. So R is obviously positive, which means the relationship between speed limit and number of accidents is positive. And this is very strong. All right, it's very close to 1. Strong, I would say, oops, sorry, I'm not writing very well here. Strong, I would say, is close to 1. Moderate would be kind of in the I would say 0.5 to 0.7 range, maybe. You can make a judgment call on that. And then weak would be under 0.5. That would be kind of the numbers that I would put on this. Maybe this up to 0.8, I'm not sure. Or you could do moderately strong once it gets to 0.7, 0.8, I don't know. But this is very strong. All right, so we're going to say the relationship, or the linear, I should say the linear, because R is the measure of the linear relationship. So the linear relationship between speed limit and number of accidents is strong positive. All right, that's what R tells us. It tells us it's a very strong positive linear relationship. You did in class. All right, so what affects R? All right, so we have X in millimeters and Y. There's no context to Y. And we want to find R. So I'm going to pause it and enter the data so that the video doesn't get too long. And then we'll kind of just keep pausing and finding R. All right, so I've entered the data here, so I'm just going to go, I did stat edit, entered in L1 and L2. So I'm just going to go to stat calc, and I'm going to do linreg, and I'm going to hit enter. So R there is 0.918. All right, so I'm going to go back here. This is 0.918. Now I'm going to change it to centimeters. All right, so X was in millimeters. We're going to change it to centimeters. That means all of these, we're going to move the decimal place 1 place. So 12 is going to be 1.2. So I'm going to go ahead and do that. All right, so I changed those all to centimeters. And so then I'm going to go stat, linreg, oops, not that one. Stat, calc, linreg, enter. And my R is still 0.918. So we can see, as I said, units don't affect R. So R has no units, so changing the units doesn't affect R. All right, it's the same data, we just changed the units. All right, so now we're going to switch X and Y and find R. I switched X and Y, I went back to the original X's, but I switched them. So now we'll do that linreg again to find R, and wouldn't you know it, R is still 0.918, because if you switch X and Y, you still have the same relationship between them. All right, so which one is the explanatory and which one is the response doesn't matter. So now change the 12 to a 22 and find R. So now I'm going to change that to a 20. So here I've kept the X and Y switched because we already know that doesn't matter. And I've changed the 12 to a 22. So then we're going to do it again. And we see now R has changed. Of course, if we change one of the numbers, it's going to change. I think that was 0.627. So we made this an outlier. So the outlier affects R. So units don't change R. Switching X and Y doesn't change R, but outliers definitely affect it. We're not going to do this example because I think we've done enough of analyzing the association. This last one, I don't have this data. Somebody else made these things, and I didn't edit this. But the example that we are going to talk about is going to be the same thing. I just don't have the actual data for it, is ice cream consumption and crime rates. All right, these are a very high positive correlation. So that means that as it's a very strong positive. So that means as one goes up, the other goes up. So if you eat more ice cream, the crime rates go up. All right. So does that mean that ice cream consumption causes crime to go up? That if you eat more ice cream, you are actually causing the crime rate to go up? I hope that you say no to that. Or the other way around, that if there's more crime, it causes people to eat more ice cream. I hope that you say no to that too, although one could maybe argue if you've gotten robbed or something, maybe you're depressed so you eat lots more ice cream, but that's not why. So correlation, the big point with this example is that correlation does not mean causation. All right, just because two things are highly correlated does not mean that they cause each other. They, in fact, could be completely unrelated to each other. What is happening here is there is actually a lurking variable that causes both things to go up. All right, so think for a little bit, what causes ice cream consumption to go up, and what also might cause, well, maybe it doesn't cause it, but what also might be related to crime rates? It is the temperature. It's the summer, right? In the summer, ice cream consumption goes up because it's hot. All right, I'm going to say summer. In the summer, or when it's hot out, crime rates go up because if it was really cold and snowy, criminals typically aren't going out and stealing cars and stuff like that. Now, do they still? Yes, but it is much more likely for crime rates to rise during the summer. That's actually something that has been researched and studied and all of that. So when it's hot outside, crime rates are higher, and so is ice cream consumption. So we have a lurking variable. We have a third variable that's affecting both of them. So that is what a lurking variable is. You've got these two variables, and then you've got this lurking variable here that's really behind the scenes affecting both of them. So to think about a lurking variable, oftentimes you have to kind of think outside the box a little bit and think, is there something else that could be affecting these two if you're really trying to say that they cause each other? So that's just something to think about, and just one example of this. I'm not certain what this example was, but this is the one that I've always used.